Thank you very much. And thank you to Guineminas and the organizers for letting me come here and talk today. So yeah, I'm from OIST in Okinawa. It's a very small subtropical island south of Japan. So this is, we saw lots of nice photos of different campuses today. So this is ours, and this is the view from my office. So if you are in the neighborhood, yeah, please call by. So today, I will talk about some work we did on correlated impurities for enhanced thermometry of ultracold gases. So I'm a member of the quantum systems unit at OIST, led by Professor Thomas Bush. So yeah, we mostly focus on ultracold atoms and looking at quantum many-body physics. So we have lots of different people from around the world, and we have some visitors all the time from Lithuania. And so we have lots of different topics that we kind of cover. And today I will talk about one thing which kind of covers non-equilibrium dynamics, some metrology, and impurity physics. So a brief outline, I will just first introduce the dephasing thermometry that we look at, and then extending this to slightly more complicated and more interesting systems. And then eventually, if we include motion and interactions in the system, can this be used to enhance or hinder thermometry of 1D Fermi gases? So a bit of motivation that we are really inspired by these Ramsey interferometry experiments that were done in Innsbruck nearly 10 years ago. So in this experiment, there is potassium impurities immersed in a lithium Fermi gas. And initially, the potassium impurities, they're, say, in the down state, which does not interact with the fermions. And then a pi/2 pulse is applied to implement the interferometry scheme. So the internal states put in the superposition of the down and the up state. The up state does interact with the Fermi gas. It induces lots of non-equilibrium dynamics. And this non-equilibrium dynamics of the fermions affects the dephasing of the impurities. And then at the end of the process, you apply an pi/2 pulse, and then you measure the impurity state to get some information about the Fermi gas. And in this case, if we take the simplest system, so we just have, say, one impurity, and we look at the density matrix of the impurity, we just have these two dephasing terms on the off-diagonal nu of t. And if we compute this for this case, the dephasing terms are just the dynamics of the Fermi gas environment, time evolving in the Hamiltonians given by the state, the internal state of the impurities, whether it's a spin up or spin down. And then the nice thing about this is that, this is a measurable quantity using this Ramsey scheme. So this is just a plot from this paper. And so the dots here, of course, are the experimental results. This is a function of time in terms of the Fermi time tau f. So what we see is that, you implement this essentially sudden interaction quench between the impurities and the fermions, and the fermions immediately start to dephase, they start to decohere. And we have two time scales here, so we have this very short time dynamics, so this is just some power law decay described by Anderson's orthogonality catastrophe. And then we've longer time dynamics, which is described by the temperature of the Fermi gas. So the different lines here, these are different theoretical models that are used. But in particular, this dashed line here, this is when we have 0 temperature Fermi gas. And of course, in the experiment, it's at some finite temperature, so this is a solid line. So we see this and we think, it's sensitive, of course, to temperature. So can we use this kind of scheme to make some good or accurate thermometer? So obviously, the dephasing is very sensitive to the temperature of the fermions. Since in this scheme, you are just measuring the impurities, you are not doing any measurement on the Fermi gas itself, so you don't have to do time of flight to, say, fit the momentum distribution to extract the temperature. So your Fermi gas arrives. So it's non-destructive or maybe minimally non-destructive. You still induce some dynamics. But you are just measuring the impurities. This is a highly, of course, non-equilibrium process. So this is an example of non-equilibrium thermometry. So we're not waiting for the impurities to thermalize with the Fermi gas. So we are just looking at this kind of fast dephasing dynamics. So we don't need to wait potentially for long times. And also, it's a very tunable system. So, in principle, we can tune the interactions between the impurities and the Fermi gas. So stronger coupling is, more destructive dynamics, which means that our impurities dephase faster. And we can play around with this and try to optimize this system. So what we did a few years ago was looking at a similar system as this experiment. So we just take one impurity. It's immobile, so it has infinite mass, so it does not move. And then what we wanted to do was to calculate the quantum Fisher information. And we want this, of course, to be large, so that we minimize the error in measuring the temperature delta T, where NM is, if we do multiple independent measurements of the system, of course, we can also improve this measurement. So for the simple case of just this two-level system, the quantum Fisher information can be written completely just in terms of the decoherence function nu and its phase phi. And when we calculate this for this immobile impurity coupled to a large Fermi gas, what we plot here is actually the sensitivity or the quantum signal-to-noise ratio. So this is just the temperature times the square root of the Fisher information. So of course, we want the sensitivity to be large. So here is the sensitivity as a function of the temperature of the fermions, and as a function of time after this interaction quench. So what we find is that, of course, at very high temperatures, we see that we get a peak in the sensitivity at very short times after the quench. This, of course, makes sense. The higher the temperature of the Fermi gas, the faster the impurities will decohere, so the faster we'll reach this maximum of sensitivity. As we go to lower temperatures, this maximum starts to move to longer and longer times. And we see that if we want to go to very low temperatures, say like a 10th of the Fermi temperature, we need to wait very long times for these low temperature fluctuations to sufficiently decohere the impurities such that we can get some meaningful signal. And of course, eventually this sensitivity will vanish as the temperature goes to zero. But it seems like this is a promising kind of application. But in this work, we take a very idealized model. So we just take one impurity particle. Again, it has infinite mass, so we suppress all dynamics of the impurity. We are just purely focusing on the dynamics of the Fermi gas that it's coupled to. So an obvious question is, what if we take more impurities, and what if they have some finite mass? So we have some kinetic energy also in the impurities, and during this interaction quench, we have motion of both systems. And is this something that can help our kind of scheme? How does it affect the sensitivity? And more importantly, what we're interested in is, can we really go to these very low temperatures and see some kind of improvement of this thermometer? So in our work, which was published at the beginning of this year, what we have two impurity atoms. In this case, these are just two spin polarized fermions. And they're trapped in some external harmonic oscillator potential, and they're immersed in a background Fermi gas environment, which is at some unknown temperature at T. So because these are two spin polarized fermionic systems, we can very simply just describe everything through the single particle Hamiltonians for the environment HE and for the system HS. And then we have some coupling between the two systems, and we take a bit of maybe a brutal approximation where we just take a density-density coupling. So here, coupled to the environment, we have the density of the impurities, which is just a sum over the single particle states of the impurity single particle wave function. And similarly for the impurities, we have the coupled to the density of the environment, which again is just a sum over its single particle states, so solution of HE. But now multiplied by the Fermi-Dirac distribution, so describing this finite temperature state. And then the coupling strength, assuming that our fermions are in this internal down state, is given just by kappa down. So we have two coupled equations. We just solve them self-consistently until we find the equilibrium states of the system. And this I show here as a function of the coupling strength. So this is the density of the environment. This is the density of the two impurities. So again, our impurities are trapped in this harmonic oscillator potential. And as we increase the coupling with the Fermi gas, in this case, we always just consider repulsive interactions. what we see is that the two impurities, they start to self-localize in space, and actually they also start to move slightly closer together. So we have some induced interaction between the two impurities mediated by the Fermi gas, which is like a weak attractive interaction. And in the Fermi gas, we see something similar. So we get this density modulation. So this like a effective double well potential that forms in the Fermi gas that further traps and localizes the two impurity states. So what we want to do is we want to play around this kind of region where we have weakly localized impurities to strongly localized impurities and look at the dynamics as we quench essentially back and forth. So what we look at initially is just taking a simple initial state, so both fermions are spin down, and then we flip them both spin up. So this is just changing the interaction strength from kappa down to kappa up for both particles. So the initial coupling, we take its kind of weak coupling, so 1.8 times the Fermi energy. And the final coupling is just doubling this. So we increase the repulsive interaction with the background gas. And then this is the dynamics of the background, and then this is the dynamics of the impurities again. And so what we see is that at very short times, nothing much happens to the impurities or the bath, except straight away after the quench. It's very hard to see in this weird color scale, but we have some density waves that propagate out from the positions of the impurities. And of course, these move at the Fermi velocity. And so at a time we give by tau I, these excitations go from one impurity to the other. And then what we can see in the impurity density is that the impurities feeling this excitation start to tightly self-localize. And then we get this kind of density waves going back and forth. And we also see that we have these very distinct Friedel oscillations get excited in the Fermi gas. So what we have happening here is, we have these bath-induced interactions that propagate between the two impurities. And we also, it's hard to see here as well, but also the impurities slowly start to move toward each other with this effective interaction term, again, mediated by the environment. We can also see that the dynamics of the impurities, they get localized, they don't disperse with time. And actually what we can show is we can write down an effective Schrodinger equation just for the impurities themselves, and we can show that the solution to this are Manakov solitons. So we have this kind of effective soliton dynamics of the impurities. And because these are fermions, these are like vector impurities, so we have some collective dynamics between the two impurity states. So this is the dynamics after quench. So this is just one of the possible scenarios that we can have. But what we are really interested in is looking, of course, at the full dephasing dynamics of this impurity state so that we can look at the thermometry scheme. So to do this, what we want to look at is, we just want to look at the dynamics of the impurity system after tracing out the environment. And we get some state that looks like this with many different contributions. So the first part here, this sigma sigma prime, these are the different internal states of the two impurities with some initial weighting rho sigma sigma prime. Then we have phi sigma phi prime. These are the motional states of the impurities after we induce the quench dynamics. And then finally we have this term here, nu tilde sigma sigma prime, which we call the Baire decoherence function. And again, this is just the dynamics of the Fermi gas environment propagating under the different Hamiltonians depending on which spin state our fermions are in. So this is exactly the same as you would see in the infinite mass case. And so to calculate this, we use a functional determinant approach, so we can rewrite this decoherence function into this determinant of a matrix A, where the elements of this matrix are just found by computing single particle overlaps of the Fermi gas environment. And then, of course, this is weighted by the Fermi-Dirac distribution function of the environment. So what this means is we can go to many, many fermions in the bath. So in this case, we take 100 or 200 fermions. So we can look at very large system sizes. And it's very efficient to compute and then also to look at the dynamics in the coupled system. So this is one quantity we want to look at, the bare decoherence function, so the dynamics of the environment after this sudden interaction quench. And then also what we want to do is, of course, we want to maybe trace out the motional degrees of freedom of the impurities and then just look at the dynamics of the internal state. This would be then similar to the Ramsey interferometry scheme. So we trace out the motional degrees of freedom. We now get a new decoherence function, nu, which we unoriginally called the full decoherence function. So this is just the bare decoherence function multiplied by the overlap of the motional states of the impurities. So what we want to do is we want to look at computing the Fisher information of both the internal impurity state, but also the full impurity state of the two impurity system, and see how sensitive this is to temperature in the different regimes. So what do these decoherence functions actually look like? So here I plot the full decoherence function in this panel, and the middle panel here, this is the bare decoherence function, so this is just the dynamics of the environment. And the last part here, this is the overlap of the motional states of the impurity. And I show this for the same dynamics I showed previously in the density. So initially, both fermions are in the down state, and then they're both quenched to the up state. And I have two sets of data here. So one is for the blue line here is for if we have light impurities. So the relative, the mass ratio between the impurities and the environment is 2, whereas this orange dashed line, this is where we have a larger mass ratio, so this is more like the heavy impurity limit. So first we just look at the heavy impurities. It's a kind of easy, trivial case. So in this case, again, we have heavy impurities, so the motion in the system of the motion of the impurities is suppressed. So this is like essentially the static limit we had before. So if we look at the motion overlap, we have some initial small decay, but eventually, like very quickly, this saturates to some constant value. And so if we look at the full decoherence function, this is mostly just given by this decay rate of the bare decoherence function, which is just, again, the dynamics of the environment. And this is just, again, described by a power law decay with some exponent alpha, which is just given by the difference of the coupling terms, kappa up and kappa down, and the reduced mass of the impurity and the environment. So again, what we see here is that there is no temperature dependence in this decay rate, so maybe these heavy impurities are not so great for this. However, if we look at the case now where we have lighter impurities, we see something very different. So in the motional state, we have these very large and distinct oscillations as the particles start to move around in the Fermi gas. And we get, again, these induced interactions, which occur in the timescale tau I, which gives us a minimum of the overlap between the dynamically evolving state of the impurities and their initial states. And then this repeats as the impurities interact throughout the dynamics. We can see in the bare decoherence function that in the Fermi gas that we have a kind of a slow initial decay rate. However, this picks up at longer times. And then, of course, if we take the product of these in the full decoherence function, again, we have these very distinct oscillations, which will give us some kind of time scale for the interferometry scheme. This is just one example of the decoherence function. We have 4 more unique ones. I don't plot them for brevity. They get more kind of complicated depending if you flip just one particle or another particle. We compute all of them into this 4x4 matrix, and then we look at the Fisher information of these different states. So this is what I show here. This is a plot again of the sensitivity. In this case, where we have these light impurities, so we have a lot of kinetic energy there. And here I plot again the sensitivity of the impurities to temperature. And we want the sensitivity, of course, to be large to minimize the error in the temperature measurement. And here I show lots of different lines, but I will quickly go through them. So we take initially, we have an equal superposition state, so all spin states are equally occupied. And we take a very low temperature of the Fermi gas environment. So this blue line here, this is the sensitivity of the full state of the two impurities. So we have the motion and we have the dynamics of the internal state. And so what we see is that, at short times, the sensitivity increases. We, again, have distinct oscillations. These are given by the timescales of these excitations through the bath, so these induced bath interactions. And the sensitivity is particularly large if we compare it to this red dotted line. So this is the sensitivity if we just take two independent impurities. So these two impurities are not correlated. So this is just the same as taking like a single impurity state with the same mass ratio. And so the difference between these two show the effect of the collective dynamics of the two impurity state, and also like the power of these induced interactions and correlations through the bath. Some other data we show here, so this orange dashed line, so this is just the internal state of our two impurities after we trace out their motion. So obviously, it's quite clear that most of the information is accumulated in the dynamics of the motional state of the impurities. So once we trace this out, the sensitivity drops pretty drastically, but we still have a pretty large advantage compared to the case of independent particles. And again, this is because the motion of the impurities has a back action on the Fermi gas, which of course affects its decoherence rate. And this yellow line I won't talk about, but this is if we do a local measurement of the internal degrees of freedom, which is suboptimal, but should be easier experimentally, and this also gives us pretty good results compared to the independent case. So what does this actually mean practically? So let's say we want a relative error of about 10%. To achieve this for independent impurities, we would have to take like 1,600 independent measurements. However, if we just look at our two motional impurities, we need around 40. So it's a big increase in the potential precision. So this is with motion, and then of course we want to check what happens when we have heavier impurities. And so again, this is the sensitivity as a function of time. And so the blue line here is for the full state of the impurities. The orange dashed line is just the internal state. Again, with heavier mass, the motional dynamics is essentially suppressed. So the gap between these two states is not that large. And also more interestingly, they significantly underperform compared to the independent case. So we see that, of course, increasing the mass, we suppress these collective dynamics, and the sensitivity also significantly suffers. So at best, we have like a factor of 5 worse sensitivity. So the system is very sensitive, of course, to the dynamics, the oscillations of the impurities, and the relative coupling terms. If we quench too large an interaction, we drive immediately to some orthogonal state, and it becomes a bit of a useless thermometer. So you need to be careful, and you need to kind of optimize. So I've reached essentially everything I wanted to say about this work. So I mean, what we investigated was the effect of motion on this on the performance of this impurity states as a thermometer. So we can see a significant enhancement. Of course, I mean, we have more information in the motional dynamics that is the temperature of the background Fermi gas imprint on this state. And we see this large collective enhancement, even though we just take our two impurities are again non-interacting fermions, but we have these bath-induced long-range interactions that can have some significant effect. However, I mean, we take a very kind of simple coupling term, so this density-density coupling. And we are really interested in looking at beyond mean field effects in these kinds of systems. And of course, this mean field coupling neglects impurity bath correlations. So what we are interested in looking at is including some impurity bath correlations, in particular in these kind of impurity polaron models. Because recent works, especially this work here, has shown that the presence of these correlations can suppress how much these impurities are localized. And so you have this kind of freezing of the localization effect at very strong coupling. And of course, this should have some big effect on the dynamics. So in this work, what they use is a correlated variational ansatz. So a two-body correlation function to describe the state of an impurity coupled to one bath particle. So we are currently looking at something similar for a multi-impurity system. And then we have some other kind of related works, also looking at impurities coupled to large baths or small baths. So we have some recent work where we have two impurities coupled to a small few-body bath consisting of tens of particles, and then using these induced interactions and correlations to create like atomic belt states in this case. And then we also have some work with collaborators looking at Bose-Fermi mixtures with DMRG, where again we can see this effect of impurity correlation, suppressing impurity localization when the correlation effects are very large. So to finish, I'd like to thank the person who did all the work, which is Sindra. So he was a student in Dublin under Mark Mitchison, who's now in King's College London, and of course Thomas Bush, who I work with. So if you've any questions, I will be happy to answer. So thank you.
So thank you, Tomasz, for interesting talk. Do you have some questions? Yes, please.
The most rudimentary possible question.
Sure.
Which is, if you want to do this in the lab, what do you actually measure?
Yes, okay. That's a very good question. So in this case, where we're looking at the full state, you would need to measure the two-body wave function of the fermions, of the two impurities, and also the internal state decoherence functions, which is hard, I understand. Yeah, so this is why we look at just the internal state. So this is just from the Ramsey interferometry scheme. So you would get you just read out what the internal state decoherence function is. And you trace out the dynamics, but it's imprinted as well on this. Another thing you can do, what we also looked at, which maybe I have some plots, is instead of measuring the full state of the two impurities, which is of course very hard, you can just try to measure the density of the two impurities. So if you can measure the two-body density, this red points. Okay, also maybe hard, but we can also just look at the one-body density, which is the green dots here. And again, this gives you some performance increase over just looking at the internal state of the system. Maybe you can't also measure the full internal state of the system, so this is why we have this green dot dash line here. This is a local measurement of the internal state. So even though you lose some information, it still gives you pretty good kind of performance. So this would be the easiest thing to measure. And then after this, it gets more successively probably difficult. Sorry.
More questions? No, yet. So maybe I can ask. Did you try to see the difference between different initial states for impurity?
Yes.
I don't know, some product state or correlated?
So actually, so what Mark and Sindra have looked at before is exactly this problem where you have infinite mass impurities, so with no motion. And so what they take is like initial belt states of two impurities. And actually, these don't perform well at all because you have strong entanglement between the two impurities, and what you want in this scheme is to create correlations between the impurities through the coupling to the bath and through the dynamics. So what they find is, starting with a product state is actually most of the time the best thing to do. You want this growth of correlations in the system rather than trying to destroy them, which is a much slower kind of process. In this work, we didn't really look at this in too much detail based on what they'd done. But we also looked at, instead of fermionic impurities, looking at bosonic impurities, for example, and we get kind of similar results. So, thank you.
More questions? Everybody is very quiet.
So maybe one more question. So if you can move the impurities.
Yeah, sure.
If you collide them, what happens?
Yeah, interesting. Yes. So we also looked at this, but you have a problem that the initial position of the impurities move too far away in the dynamics. So this motional overlap will, in that case, vanish. and your signal then essentially goes away. So you want a bit of motion, but like around their initial positions, essentially. Like you cannot have them moving everywhere in the system. This is you then just you achieved some orthogonal state, and it's not great. So.
One more quick question. Okay, so if not, let us thanks to Tomasz again.